Hi, I'm Aditya and I'm the CEO of Automatski. Automatski makes the world's most powerful quantum simulators, annealers, and computers. Today I'm going to demonstrate graph coloring to you and I will keep it extremely short. I assume you already know the theory and applications, and I assume Automatski has given you the context of this video. So you will understand what I'm going to show you. If you received this video by mistake and don't know what this is all about, just ignore it. I'm here to tell you what we have achieved and not how we have achieved it. All our millennium breakthroughs are completely our own inventions without any collaboration or help from absolutely anyone else. The implementation details of our inventions will remain a secret for the next 1,000 years. If that doesn't work for you, you should stop watching this video right now. Okay, let's get started. What is graph coloring? So in mathematics, we call a graph as a general structure where vertices are connected to other vertices. And in this problem of graph coloring, the graphs can be connected ad hocly, without any fixed structure. And the problem is to define the maximum number of colors you can use to color the graph. Let's say 3 or 4 or 5 or 20 or 100 or whatever. And then using only these color numbers, assign colors to all the vertices of the graph such that no two neighboring connected vertices have the same color. If two connected vertices have the same color, it's a conflict, and that is not allowed. Besides this, you should be able to set a certain number of vertices to a fixed color value or a range of color values. That's why we are using a constants file here to do that. Now, the classical NP-complete problem of Boolean satisfiability can be mapped to graph coloring. So graph coloring is also NP-complete, though it is not used very popularly to solve NP-complete or NP-hard problems. But this is something that is very powerful, and today we are going to show how we solve this using our quantum system. All our quantum systems are hosted remotely in our data centers and can be accessed by front-end programming languages like Java, Python, Rust, or Mojo or whatever. So programming languages is not an issue. This is a Java IDE which will be responsible for loading up the problem into the remote solvers and showing the solutions. So if the max colors are 4 and I have a test graph of 100 vertices, this graph is stored in a Dmax file. Dmax is a standard for storing graphs. This is what it looks like. Edge number 1 is connected to edge number 40 with a weightage of this. In graph coloring, we don't use the weightage normally, so it doesn't matter. But this is a general graph structure file where it says which graph is connected, which vertex is connected to which vertex. So let's run this and see how it goes. So the maximum number of colors allowed were 4. The number of nodes was 100. The number of edges was 242, and the operations it took was 992. And then it sampled and got a result, and in 0 seconds. The results are stored in a file. This is what the results look like. Node number 1 is colored 0, node number 2 is 2, and so on. All the 100 nodes are colored, and the total time taken is 0 seconds. Now, the problems that are we at Automatski benchmark with a lot of problems. These are all Dmax implementation challenge problems mentioned here, which we benchmark with. Okay. Now, those problems are tough, and that is why it tests the accuracy of the solver. But for scale, our system this is a non-production grade system, so it is 1,000 times cheaper, but also 100 times cheaper and 1,000 times slower. But it allows us to test our problems at scale, and with graph coloring, it almost always solves the problem even in a test environment. Let's try a larger problem. I am going to set the maximum number of colors to 5 because it is unsolvable with 4. Finding the chromatic number of a graph, arbitrary graph, is NP complete. Okay, just so let's run this. So number of colors is 5, number of nodes is 1 lakh, number of edges is whatever, and after this I'm going to run a larger problem. We call this mid-size problems. These are in the range of 1 lakh vertices, 1 million vertices. For us, we can extend the range of problems to 100 million vertices or qubits or whatever. 100 million, 1 billion, or even a trillion in some cases. So it solved it in 31 seconds, and let's try a bigger million qubit problem. So it takes a while to load. I'm going to pause it because it is going to take some time, and then when it finishes I'm going to resume. And it has solved the problem. It took 587 seconds. This is a test environment, and it is 1000 times slower than a production environment where it'll give answers in split seconds. Now you must have heard of problems like max k cut, which is equivalent to maximal graph coloring, trying to color as much of a graph with the given number of colors. So that's all we had for today, and using graph coloring we can solve NP hard, NP complete problems. It's a great way to solve such problems on a quantum system. We are not using a classical algorithm like simulated annealing or Markov chain, Monte Carlo, or some probabilistic method or flipping methods or some such. Our system is based on quantum phenomena, and that's all we had for today. If you have any questions, please email us at info@automatski.com. Thank you.